Alright, so we are on question 9 of the November 2018 South African CAPS syllabus mathematics matric exam, and this is paper 2. Right, we're on question 9 and some more Euclidean geometry. Quite a few of these Euclidean geometry questions in paper 2, so it's good to know your theorems. Okay, let's have a look at this question. So it says in the diagram JKLM is a cyclic quadrilateral, as we can see, and has a center of O. Now we need to prove the theorem which states that angle J plus angle L together make 180. So that's the theorem we should know, and now we have to prove why that's true. Okay, so I would suggest let's connect some lines here. Let's do KO and OM. Right, and how this will help us is now we know the following. Let's say we call this angle O2 and this one O1. Okay, so now there's some other theorems that we do know that we can use. So we know that this angle is double that angle, right? And the other way around for this one and this one. So what is the reason? So we can say angle O2 is equal to 2 times angle J. Right? O2 is 2 times angle J, and our reason for that is the following theorem. Angle at center is 2 times the angle at the circumference, right? So just quickly again, we draw a circle just to show. So if we have some circle, and from somewhere we draw a point, or let's say that's the center. Let me actually draw the center in, the center. Now if we connect to the center, make a triangle-ish thing like this, a sector, and from the same points, from A, B here, we draw it to the circumference, anywhere on the circumference. We can even draw it here, right? And then connect back there. Then we know that the angle at the center, this angle, is double this angle, right? Angle at the center is double the angle at the circumference, right? So if this was x, this would be 2x. And you can draw it anywhere, right? Let's use another color and let's just draw from the same point. Let's draw it to there where it maybe looks a little bit easier. Then again, same thing. If this angle is 2x, this angle is x. Angle at the circumference is half of the angle at the center, or angle at the center is double the angle at the circumference, which is what we have here. From this KM, from this arc, we go to the circumference, and we go to the center. Right, so angle at the center is double the angle at the circumference. All right, now let's use pink for the other one. Let me actually just move this out of the way. We'll move that over there, and let's continue. Now we also know that the opposite is true. Angle O1 is equal to 2 times angle L, right? O1 is double angle L. And it's exactly the same reason. So we're going to write the same reason. I'm just putting these two lines to show it's the same reason, but you probably have to write it out. Okay, and now what else do we know? We know this together, O1 plus O2 is a circle, right? So you know angle O1 plus angle O2 gives us a total of 360 degrees, right? And that's just angle of a revolution or a full circle. Let's call it angle of revolution. Yeah, this is probably fine if you don't write this because it's obvious that a circle makes 360, but just in case. Okay, now, but we know O1 is 2L, so we can replace O1 with 2 times angle L. Plus, and O2 was 2 times angle J. So we can replace O2 with 2 times angle J. And we know that has to be 360. Now let's factor out a 2. So 2 times angle L plus angle J equals 360, and divide by 2 on both sides. So if we divide both sides by 2, then we get angle L plus angle J equals 180 degrees. Alright, so that's the basic idea. We want to connect two lines to the center and then show that angles at the center is double the angle at the circumference. We want to use that idea and solve for L plus J from there. Okay, let me know if you found a different way to do it. I think this is probably the most standard, normal way to do it. But you could have also done something, instead of using all these letters, you could have just said, let's call this x, and then, well, let's call this x, then that would be 2x. Let's call this y, and that would be 2y. And you can just say 2x plus 2y is 360, and do the same thing instead of using O and L and J. All right, let's move on to question 9.2. Okay, in the diagram, a smaller circle ABTS is given and a bigger circle BDRT. So BT is a common chord. BT is a chord of both circles. As we can see, it's a chord in this circle and it's a chord in the bigger circle. Straight lines STD, and ATR. ATR are given. Chords AS and DR are produced to meet at C. Okay, we can see that. And BS and BD are also drawn. Okay, and they give us angle A is X and angle R1 is Y. Great, so all the information is in the picture. Let's see. 9.2.1, question A. So name and give a reason to find another angle also equal to X. So if this is X, which other angle do we see that's equal to X? Well, that is going to be angle B1. Angle B1 is also equal to X, and the reason for that is angles in the same segment. Angles in same segment. Same segment. Okay, let's quickly see what that looks like. The idea is if we go from any point, pretty similar to the previous question, except now both angles will be on the circumference. So from, let's call this A and B. So if from A and B, from this arc, we draw two triangles, so there and let's say there, then these two angles will be the same, right? So it's going from AB and from AB. And we could draw another one, let's say from there, right? So still from AB, so this angle will also be the same. So it doesn't matter where you draw it. All these angles will be exactly the same. So that's the idea of angles in the same segment. You could also say angles subtended by the same arc. That would also be the right way to give the reason. Okay, let's move this out of the way a bit. Where should we put it? Well, let's just put it there, that's fine. Okay, 9.2.1 number B. 9.2.1b. Now we need to find another angle equal to y. So we know this is y. Which other angle would be equal to y? And again, for 2 marks, it's again just an answer and a reason, so it's a simple, straightforward, a single reason. We don't have to do calculations. But we do need to know a lot of theorems, right? We do need to know all the theorems so we can just spot the answer. Now if this is y, then this angle B2 would also be y. So B2 would also be y. And our reason for that is exterior angles of a cyclic quadrilateral. So let's first write that down and then I'll explain. So exterior angles of cyclic quadrilateral. I'm just going to write cyclic quadrilateral. Okay, so if we have a circle, so we have that circle, and we draw some lines in it. So we draw a cyclic quadrilateral, something like that, and then let's just continue this line. Okay, what do we know about a cyclic quadrilateral? We know opposite angles are equal, sum to 180. So let's say if this was angle X, then this would be 180 minus X, right? Now, this is a straight line. So if this is X, this is also 180 minus X. So that's why we have the exterior angle is equal to the opposite interior angle of a cyclic quadrilateral. So that's what we have here. If we look, let me just highlight what quadrilateral we're working in. So we're working in this one here. And let's continue the straight line here. Okay, so we see if, so this angle is equal to this angle, right? This angle equal to that angle. Because these two make 180, so the difference between them will be the same as this one here. Alright, let me know if I didn't explain that well, but hopefully it makes sense. If these two sum to 180, so let's maybe just do that again. So this is y, then this is 180 minus y, because of angles in a straight line. And these two together make 180, so that one would be 180 minus this angle, which is 180 minus y. 180 minus 180 is nothing, and minus y is positive y. So we see that's y, and that's y. All right, I hope that was clear enough. Let's just get rid of those. And then we can move this out of the way. Yeah, we can move. Actually, it's probably fine. We can just keep it over here next to the question and get on to the next question. 9.2.2. 9.2.2. Prove that SCDB is a cyclic quadrilateral. SCDB, let's just highlight that again. SCDB. So we must show this is part of a cyclic quadrilateral, which means the circle will fit right around its edges here. Yeah, how do we know if something is a cyclic quadrilateral? Well, like we just saw, if the opposite sides of a quadrilateral sum to 180, then it's a cyclic quadrilateral. Right, so let's find that. Let's say I'm going to find angle C and angle B, right? Because we have B1 and B2. So B1 plus B2. B1 plus B2 is what we already found those, right? B1 was also X and B2 was also Y. So B1 plus B2 is X plus Y. Right now, so we know that is X plus Y. X plus Y. Now we need to find angle C. What do we think? How do we think we'll find angle C? Well, I would suggest we've got a nice way to do that. A very quick way. We can look at this triangle. This triangle here. Right, and what do we notice? We notice we have one angle, we have another angle, so we can find the third one. Right, so angle C is equal to 180 minus X minus Y. Minus X minus Y. And the reason for that is that angles, or some of the angles in a triangle, some of angles in a triangle. The sum of angles in a triangle add to 180. So these three together must give us 180. So that's what we have for angle C. And now let's just rewrite that by factoring out a -1. So it's 180 minus X plus Y. Okay. So now we can see if angle C, so 180 minus X plus Y. So if these two together make 180, it's a cyclic quadrilateral. So let's see, what does it give us? So angle B1 plus B2, B1 plus B2 plus C, let's check. That should give us 180 if it's a cyclic quadrilateral. So B1 plus B2 is X plus Y, so we've got X plus Y, plus, and then we've got angle C, which is 180 minus X plus Y. Alright, so X minus X is nothing, Y minus Y is nothing, and then we're left with 180. Perfect. So that is a cyclic quadrilateral. And our reason, so let's just write that down. We want to say SCDB is a cyclic quadrilateral, a cyclic quad. And our reason is, again, this reason. Opposite angles in cyclic quadrilateral. In a cyclic quadrilateral. Right, so opposite angles in a cyclic quadrilateral sum to 180. We showed that it sums to 180, which means this is a cyclic quadrilateral. Great. Then on to question 9.2.3. 9.2.3. Okay, it is further given that D2 is 30. Okay, so this part here is 30 degrees. And AST is 100. AST. So this part here, that's 100. 100. Okay, prove that SD is not a diameter. SD is not a diameter of this cyclic quadrilateral that we found. Okay, so for this question, we need to consider the following. I'm going to draw another quick circle here just to show something. So if we had a diameter, let's say that was a diameter, right? So it goes straight through the center. If that was a diameter, then if we draw this, right? So we've got some cyclic quadrilateral. And if this line straight through was a diameter, then we'd have the following. Then this angle would be 90, and this one would be 90, right? Because angles in a semicircle make 90-degree angle. So let's see. In our case, if this is the diameter of a circle, let me actually see if I can draw a circle that's sort of big enough to cover that. Let's do that. Make it slightly bigger. Okay, and what happens if I draw this over here? Oh, no, it's too big. I'm gonna make it a bit smaller. I just want to get sort of an idea here. Something like that. Okay, so our circle should be roughly there. Something like that. Alright, so if this is our cyclic quadrilateral, and let's draw everything in red now. Everything in red. So we know what we're busy with. Okay, so in this cyclic quadrilateral, so we have to prove that this SD is not a diameter. If SD was a diameter, then this would be 90 degrees, this would be 90 degrees. Right, so if we can show this is not 90 and that's not 90, then we've shown it. Alright, so let's quickly just erase some of that so we can see our picture again. So we know that is 100. So we can say S3, this part then will be what? 180 minus 100, so that'll be 80 degrees. So let's start with saying S3, oopsie, S3 is 80 degrees. Okay, and that'll be because of angles on a straight line. Angles on a straight line. I'm just going to do that for a straight line for now. So we know that's 80 degrees. 80. Okay, what else do we know? If this is 30 degrees, let's use now triangle SDC, right? This triangle. So we know that's 80, that's 30, so then we can figure out what angle C is. Right, so in triangle, let's just show which triangle we're working with. In triangle SDC, we want to say that C is equal to 180 minus, what are the other angles that we know? Minus 80 minus 30. Oops. Okay, minus 80 minus 30. So that gives us an angle of 180 minus 80 is 100, minus 30 is 70 degrees. 70 degrees is not 90. Okay, and just the reason is again angles in a triangle, sum of angles in a triangle. Okay, so we see angle C is 70 degrees, so it's not 90. Right, so that's the first part. Now let's also show, I think this should be fine actually, but let's also show the other one. Let's also show angle B. So we know angle B plus angle C, we found that is 180, right? So angle B plus angle C equals 180. And we know what C is now, so angle B equals 180 minus C, which is 70, the angle B equals 110. And that's also not 90. Right, so we've shown this angle here is 70, and we calculated this angle here is 110. Now if this was a diameter, then this would have been 90 and this would have been 90. Alright, so we can say SD is not a diameter. So SD is not a diameter. And the reason is because it does not subtend a 90 degree angle. So it does not subtend a 90 degree angle. Okay, if it was a diameter, it would subtend a 90 degree angle, but it doesn't. So that is our reasoning here. Good, so Euclidean geometry, you can see there's quite a few theorems that you have to know. You have to be able to spot things. So it takes a bit of practice and a bit of studying to know your theorems. Alright, so that's it for question 9, and I'll see you again for question 10.